Bismillahir Rahmanir Rahim. Welcome to this session of EE206, Introduction to Electrical Systems and Computations. This session is dedicated to the topic of signal processing. What is signal processing? Signal processing is basically the application of mathematical algorithms on either analog or digital signals to achieve a specific purpose or a specific objective. So, what are some of the applications that use signal processing? In fact, the applications are countless. There are so many applications that use signal processing, but there are some applications that are famous, and you may have seen some of those applications without knowing that huge amount of signal processing goes into those applications. The list that you see in front of you there is just a small list of applications that use signal processing. One of the applications, for example, is communication systems. In fact, the mobile phone that you have in your pocket is one of those devices that use huge amount of signal processing to produce to you the sound of the other person that you're talking to. Control systems in factories as well as plants and so on often employ huge amount of signal processing to control the different processes that go on in the plant. Yeah? Data storage systems, for example, if you have a hard drive in your computer, there is a lot of signal processing that goes into storing the data in the hard drive as well as retrieving the data back with the minimum amount of errors and so on. Okay, so this is also another application of signal processing. Seismological exploration of oil and gas is one of the famous applications that use heavily signal processing to basically determine the possibility of having oil in a specific region. Medical imaging systems. If you have ever gone to a hospital and your doctor requested that you do an MRI or a CT scan or ultrasound, all of those applications or all of those imaging devices, medical imaging devices, use signal processing heavily to produce the image that your doctor will use to diagnose you. Speech processing as well as image processing. Those are two applications that all cameras, for example, the camera that you're watching me on, as well as my voice that you're hearing now, have been processed using the camera heavily, using some image processing as well as speech processing algorithms to be able to provide you with the highest quality video as well as the highest quality audio. And as I mentioned, this is just a small list of applications that use signal processing. There are many applications that also use signal processing throughout, everywhere you look. So in this video, we will concentrate on two of those, and I'll give you more information on them. The first one being the seismological exploration of oil and gas, and the other one being image processing. So let's start with seismological exploration of oil and gas. Now, the picture that you see in front of you there represents a cross section of a specific region in which there might exist oil and gas, but for someone who's living on the ground, he may not be aware of the existence of those. Assume that you were asked to determine whether there's oil or gas under a specific region. One option that you can do is you can put an oil rig there and start drilling and hope that you'll hit a reservoir that contains either oil or gas. The problem with this is that it's very expensive to go and dig, because either you may stop before you reach the oil or gas, okay? Or worse, you could keep digging and digging and digging and going deeper and deeper, and eventually determine that there is no oil or gas in that region. Okay? So clearly this is not the best way of searching for oil or gas or any other resources under the ground. So what do? Long time ago, oil companies used to employ geologists, still they do, but in the past they used to depend on geologists who would survey the ground in a specific region and determine what types of layers exist under the ground, and based on this they would determine, for example, the probability or the regions where high probability exists for finding those natural resources. Nowadays, we can actually have a better view of what's under the ground by applying specific signal processing algorithms that will allow us to give us better view of what's under the ground. Okay? So what happens in today's exploration of oil and gas? The concept of seismology, which is basically sound waves that travel in the ground. Okay? The concept there is used to give us a better view of what's under the ground. So an oil exploration company would usually bring something called a vibrator track, similar to the one that you see in front of you there. Okay? And it will also bring a recording track, and I'll talk about the purpose of both of those. Okay? And it will plant in the region in which they want to explore a set of geophones. The set of geophones that you see in front of you there is a linear set of geophones, basically in a line. But usually, geophones are planted in the form of a matrix. A matrix that is planted in the X as well as the Y dimension. So what is going on there, or how will this equipment be used? The purpose of the vibrator track is basically to produce vibrations, or basically sound waves, that will travel in the ground. Whenever sound waves travel in the ground, they may hit barriers, or they may hit the boundaries between different layers in the ground. So as those sound waves hit the boundaries between the different layers in the ground, part of those sound waves will reflect back, and they will be captured by the geophones. The geophones will take that information, send it to the recording track, which will record all of the vibrations that have been received for later processing. Okay? So imagine that we have a vibrator track, and it's producing sound waves. Those sound waves will penetrate the ground and will travel very deep in the ground, several kilometers down. As those sound waves travel, they'll hit, as I mentioned, the different barriers, okay, between the different layers. And as the sound waves hit the different barriers, they reflect back. So let me just focus on the middle path that I have there. In fact, I'm showing there only 3 paths, but in reality, there are millions of paths over which, or the sound waves will travel over. Okay? So I'm focusing here only on the middle path. So assume that I have sound waves that are traveling over the middle path. What will happen is, as those sound waves hit the different boundaries between the different layers, they reflect back to the different geophones. Let me play this again for you. So if you notice, the green dot represents the transmitted sound waves, and the orange and blue and the purple dots represent the sound waves that are reflected back to the geophones. If you notice, let me play it again. If you notice, as the reflected sound waves travel back, they reach the different geophones at different times, because the geophones are located from the reflection points. They're located at different distances from the reflection points. Let me play it for a 4th time, just to show you. So for example, the first geophone will receive the signal, while the last geophone has not received the reflections yet. Okay? And all of those reflections are being recorded by the geophones and transmitted to the recording track. So what the recording track will do now is it will collect all of those reflections from the millions and millions of the paths that have been traversed by the sound waves. Those recordings will be taken to a computer that will process all of those to come up with a picture of what's under the ground. Because of the complexity of this configuration, usually supercomputers will be used, and after a couple of days or so of processing those reflections, an image similar to this will appear. To you or me, this may not mean much, but to the eyes of an expert, this basically will indicate very clearly the possibility of oil or gas existing under specific layers. Okay? So once the expert looks at an image like this, he will have, with very high certainty, he will be able to, with very high certainty, to say, for example, that a specific location, there is high possibility of having oil or gas under the ground. This was not possible to achieve without the application of huge amount of signal processing and very complicated algorithms of signal processing that generated this from the reflections that were captured by the geophones. So this is one application of signal processing that is very widely used by oil and natural gas exploring companies. The other application that we're going to be talking about here of signal processing is using signal processing in the field of image as well as video compression. First, let's talk about how digital images and digital video is stored on a digital device. Images are stored on a computer in the form of a matrix of pixels, where a pixel is that small square that represents one dot of the image. So a typical image, for example, could contain 2,000 pixels across and 1,000 pixels vertical. Okay? So this will mean that a picture, for example, contains 2 million pixels, where, as I mentioned, a pixel is basically that small square that represents the smallest element of a picture. Usually, the number of pixels in a square image of a picture is represented, or basically this is what we call the resolution of the picture. Okay? So you could look at two computer screens that have the same size, but one of them has higher resolution. What does it mean? It means that the number of pixels per square inch of that screen is higher than the other screen. Now, how are digital videos represented in a computer? Basically, digital video is represented as a series of still pictures. Okay? And usually, the number of pictures per second that constitute or that make digital video is generally 30 frames per second. Now, each pixel, if you look close, each pixel is made out of 3 different colors. Okay? The red, the green, and the blue, or basically what is usually abbreviated as RGB. So each pixel, to represent each pixel, we need to have a value for each one of those 3 colors. A value for the red, a value for the green, and a value for the blue. So basically, each pixel now requires 3 bytes, where 1 byte is dedicated to the red color, 1 byte is dedicated to the green, and 1 byte is dedicated to the blue. So this picture basically shows you a zoom in to a computer screen, and if you look at the small box that is zoomed in, you see that there is a sequence of red, green, blue, red, green, blue, red, green, blue. Each group of red, green, blue basically represents 1 pixel. The series of red, green, blue will allow you to represent all colors starting from black, where the value for each one of those, for the value of the byte value of each one of those becomes 0, 0, 0. This will produce to you a black color, and if you have the other extreme, which is the white, you have the maximum value for a byte, which is 255, for each one of those 3 colors. This will give you basically the white color. And all colors between the black and the white are represented by different ratios of those 3 colors. Now, one of the things that concern us here is the size of a high definition colored image and the size of high definition video. Consider, for example, that you have a high definition colored image, and high definition colored image basically means that the image has a resolution of 1920 by 1080. This is basically the standard size of a high definition image. If you multiply the number of pixels in the row by the number of pixels in a column, you'll end up with more than 2 megapixels or 2 million pixels in that image. And we've just mentioned that each pixel requires 3 bytes of data, 1 for the red, 1 for the green, and 1 for the blue. And as such, you will require an amount of data to store that image that is equal to more than 6 megabytes for that single image. Now, this by no means is the highest resolution of images that you can see. In fact, many mobile phones nowadays can take pictures with much higher resolution than this. In fact, some mobile phones now have cameras that have resolution of 10, 15, even 20 megapixels, which means that you're talking about a resolution which is 10 times higher than the resolution that we're talking about here, which means that a single image will require, roughly speaking, 62 megabytes of data to store, theoretically. Okay? 62 megabytes of storage, this means that just taking 10 or 20 or 30 pictures will fill up the memory in your mobile phone, which is clearly not practical. Now, if we go to high definition video, as I mentioned, is just a series of high definition images, and you're talking about 30 images per second. So you're talking about the same number of pixels per image, which is slightly more than 2 megapixels per frame or per image, and 3 bytes per pixel. You'll end up with the same number of bytes per frame in the video like the high definition colored image. Okay? So you're talking about 6.2 megabytes per frame. Just consider, for example, 1 second of video, then you're talking about 186 megabytes of data to store 1 second of that high definition video. Okay? Imagine that you're talking about 2-hour video or 2-hour movie, for example. Then you're talking about more than 1.3 terabytes of data just to store this 2-hour high definition video. Clearly, this is not practical because typical hard drives that you could buy from the market nowadays have a size of 1 or 2 terabytes. This means that you're talking about one hard drive just to store one video of high definition. So knowing that you need huge amount of storage to store images and video in their raw format, how can signal processing be used to compress images? Okay? One of the things that you can use signal processing is to take an image in its raw format, basically the values of pixels, and you can compress that image into a smaller size, store it, and then whenever you need to view that image, you can uncompress it. Okay? So basically, this is the concept of image compression. Image compression has one of two formats. One of them is called lossless compression, and one of them is called lossy compression. Okay? We'll talk about each one of those in a minute. But the concept is how can you achieve compression of images? If you look at an image, very rarely pixels will change value. For example, if you look at my body here as you're watching me, you'll see, for example, that the edge there, my thobe here has white color while the background, for example, is brown or beige or something like that. Okay, so there is a sudden change from this color to the color of the background. But if you look, for example, at my hand here, the pixels, adjacent pixels, almost have the same color. So the concept here is to try to reduce the amount of data that you need to store for regions where the color is almost the same by applying some signal processing algorithms. This is not that different from the following. If I said, for example, the following, hello, 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 hello. If I said hello 10 times, and someone asks you, what did I just say? You have one of two options. You can either say, he said, hello, 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 again, just like I said it, okay? Which will require you, for example, 10 seconds, 1 second for each one of the hello that I've mentioned. Okay? Or you can say it in another way, where you can say that he said hello 10 times. Okay? Clearly, saying that he said hello 10 times will require much less time and much less storage than saying the hello 10 individual times. Okay? So basically, this is the concept here. Things that are repeated, you can just store one of them and how many times they have been repeated. This is basically more or less the concept that signal processing algorithms use to store images with using a smaller amount of data. Now, what's the difference between the lossless compression and the lossy compression? In lossless compression, when you take an image and store it and then retrieve it back, you get an identical copy of the original image with no change at all. Okay? While in lossy compression, you start with an image, you compress it, and then when you uncompress it, you get an image that is close to but not identical to the original image. Okay? The fact that in lossless compression you get exactly identical copies of the original as well as the uncompressed image, result in having only small compression ratios. Roughly speaking, a ratio of 5:1, which means that if you start with an image that has a size of, for example, 5 megabytes, you end up with a compressed image that has a size of 1 megabyte only. Okay? But if you apply lossy compression compression algorithms, you can end up with an image that requires 1/50th of the original size. So you start with an image that is, for example, of a size of 5 megabytes, and you end up with an image, a compressed image, that only requires 100 kilobytes or so. Okay? What's the difference in the algorithm? In lossless compression, only redundancy is removed. Okay? While in lossy compression, the algorithm understands that the human eye can distinguish or is sensitive to edges of objects, is highly sensitive to edges of objects, but it's not sensitive to regions in which the colors do not change heavily. Okay? So it uses this fact to achieve very high compression ratios. Now, what about compression of videos? As we mentioned, a video is nothing but a series of still images. So video compression is more or less the same concept as image compression, but there is also one thing that is used by video compression to achieve that huge compression ratios in which you end up with a compression ratio of sometimes 500:1 or so, especially in specific videos. You can compress them with huge amount of compression ratios. What is that other feature of videos? It's the fact that the video is a sequence of frames, and very often a frame and the following frame and the frame before it are almost identical to each other with very small differences. Okay? So video compression algorithms use basically the fact that consecutive frames have very small differences between them. So they store a frame, they compress it and store it, and then they say that the following frame only has changes in this region and changes in that region. And the following frame has a difference compared to the previous frame that has changes in other two regions and so on. Okay? So by doing this, you end up with an image, and the following images are almost the same as the previous image, with only small additions or modifications to the original image. By doing this, you can achieve huge compression ratios that, as I mentioned, could reach, for example, a ratio of 500:1. So you start with a video that is of size 1 terabyte, and you end up with a video that is only a size of 1 or 2 gigabytes or so. Okay? So basically, by doing this, you end up with huge compression ratios for videos. Okay? So in this video, we have talked about signal processing in general. We have talked about different algorithms or different applications that use signal processing. And we have focused on two applications. One of them is the seismic exploration of oil and gas, and how signal processing is used in being able to determine with high probability the existence of oil and gas in a specific region. And the other application that we have talked about is the use of signal processing in video as well as image compression. Thank you so much.